All right, so today we are going to be covering inverters. They're all inverters can be broken down into the energy source that they come from. Are they a battery based inverter or are they a grid tied inverter? A grid tied inverter means that the MPPTs are built into the inverter and the array is connected directly to that inverter. All inverters can also be broken into the ways in which they create their signal. The terms line commutated or load commutated will be discussed after a while. But there are smart inverters that can do both. They can be both line commutated and load commutated. Those bimodal or multimodal inverters are capable of exporting additional power that is not needed back into the electrical grid and capable of running emergency loads or backup loads in the event of grid failure. So, what is the purpose of an inverter? The purpose of an inverter is to convert DC or direct current into AC or alternating current. Direct current obviously flows in one direction, from the negative to the positive. Alternating current is current that changes directions from a positive to a negative. It has a wave form, a frequency, and a magnitude. In other words, what do the electrical characteristics that are coming out of the inverter look like if we were going to graph them on a graph or look at their signals on an oscilloscope? Some of them can be square. They can still be AC, but be square waves or square signals. On, off, negative, off, on, off, negative, off. That's AC electricity. But modern inverters have to match the sinusoidal wave form of the grid exactly within 2 to 3%. And so almost all modern, especially more expensive or high quality inverters, are going to output a modified square wave or a true or pure sine wave. The waveform is the electrical signal that varies over time, and it should repeat periodically. Our waveforms for the US system repeat every 60th of a second. So we have 60 hertz AC, and in 1/60th of a second, the waveform starts at zero, rises to its peak voltage, returns to zero, drops to its peak negative voltage, and returns to zero. All of that happens in 1/60th of a second. All right. The European system operates on a 50 hertz system. So one cycle there is only 1/50th of a second. Why do you think that they use 50 hertz and America uses 60 hertz? To be different?
Yeah, I don't know.
Well, the metric systems that they use are all based on tens, and so a 50 hertz system works and combines very well for multiples of 10. However, in the United States, we are the ones that kind of created these signals, and so we have 60 minutes in 1 hour. We have 60 seconds in 1 second, and we have 60 cycles. Sorry, we have 60 seconds in 1 minute, and we have 60 cycles in 1 second. All right. That was the reason that they picked that back then. And so the interval of time between the beginning of each wave pattern is the cycle. So wave forms can be viewed visually using a device called an oscilloscope. We do not have the time in this class to actually get an oscilloscope out and study the waveforms. I have at least 3 oscilloscopes that are up there, and any of you that would like to use some of your outside lab hours to get to know one of the oscilloscopes, you're totally welcome to spend 2 hours of lab time, but it would need to be in here. I would need to see that you had successfully made some progress and you could actually visualize the waveforms that were coming out. Now, I will tell you that an oscilloscope is an unbelievably handy tool for advanced electrical issue diagnosis. In fact, every vehicle that has a computer that will put out codes that you can hook up a code reader to, all that code reader is doing is reading the electrical signal sent out by this device. With an oscilloscope and proper training, mechanics can actually read those codes, look at books, and see the codes for every auto manufacturer, even without having a code reader for that automobile. All right. So there's all kinds of things that you can decipher using an oscilloscope. Yeah, an oscilloscope and Google, and you're an electrical engineer. Yeah. So sine wave is a mathematical function of a trigonometric sine. I'm not going to make you use the sine function for any math in this class. It's just not applicable to solar design or installation. If you actually go on to be a solar equipment developer, you're going to get probably a bachelor's degree in electrical engineering, possibly a master's degree, and that's when you're going to get into the sine and the math of these wave forms. Mainly, I want you to be able to understand the different parts of the waveform. To start with, my distance from here to here on this chart is actually a representation of time. All right, how long did it take time-wise from the start to the end? Now, this could be measured by one point to the next anywhere. I could start at this 0 and go to this 0. I could start at this bottom and go to this bottom. But all in told, one wavelength should take 1/60th of a second. All right. We also have the mean amplitude, the RMS amplitude, the peak amplitude, and the peak to peak amplitude. Now, these numbers can be a little bit confusing if you have not taken an introduction to electronics class. But in your introduction to electronics class, you should have done, or you should do, RMS and peak calculations. All right. The main thing that I want you guys to understand right now is when we talk about the voltage of a system, it's 120 volts in the wall. We are talking about the RMS voltage of that system. We are not talking about the peak voltage of the system. It's one of the reasons that the wires that are inside of our walls are rated to handle up to 600 volts of AC. All right. Now, typically you think, oh, they're only handling 240 volts. That's the 240 volts is the RMS. The peak is going to be noticeably higher than that. And so that's part of the reason that the wires in the wall aren't only rated to handle 250 volts. They're rated to handle all the way up to 600 volts. All right. Just for either show of hands or voices, how many of you guys right now, if I gave you the RMS voltage, do you think that you could figure out the peak voltage without Googling it? No one? Okay. All right. Then that lets me know where you guys stand on that. Do you at least understand the concept of what the RMS voltage is versus the peak voltage? Or do we want to briefly talk about what's the real difference between those two? Like, why do we even have the RMS? Do it? I would like to. Okay. All right. So peak voltage is pretty obvious. This is the highest voltage that it ever achieves. RMS voltage is the equivalent to the work that can get done by a DC voltage source. In other words, if I had 120 volt DC battery and I hooked it up to this electric motor, and I had AC electricity hooked up to this electric motor, what voltage of AC would put out the same amount of power as 120 volt DC. So AC voltages that are listed as RMS voltages are the root mean square. Basically, this is the amount of work that would get done if I had 120 volt or a similar voltage in DC. Does that make sense now? A little more? Why does that happen? Because right here there is no work being done. Right here there's no work being done. Right here there's no work being done. And all this space close to that, there's very little work being done. Why? Because there's very little voltage. I start at 0 volts and then I increase all the way up to my peak and then I decrease all the way back down to 0. And then I go to my negative and I go to 0. So right here and right here and right here and right here, there's no work being done. Well, if this motor has to constantly put out a certain amount of power and a DC power source is constantly feeding power into there, I'm going to have to give it more power on some of the points to compensate for the lack of power at other points. All right. So whenever we say the peak voltage is 180 volts, well, the RMS voltage is going to be about 120 volts, which is basically saying that it does the same amount of work as 120 volt DC power source. A little clearer now? Very much. Awesome. Peak to peak is merely the highest voltage to the lowest voltage, and it is equal to peak times 2. All right. I don't think that in any of the NABCEP tests or my tests, you are actually asked to do RMS to peak calculations, but it is a very simple number. I think it's like 0.77 or 0.67. I don't know it off the top of my head because I don't do that math all that often. But I'm very confident, knowing your guys' math skills, as soon as you had that factor, that conversion factor, you'd be able to do these conversions just fine. Why do we use sinusoidal AC? Well, to start with, that's the type of AC power that we created. All right. And so if I draw a circle on the board that is a representation of a rotational generator, right here, my magnets are moving in this direction. Right here, my magnets are moving in this direction. Right here, they're moving in this direction, and right here, they're moving in this direction. Let's say that as they move this direction, they are cutting. How about this? I'll just draw a line like this. This is my conductor. When my magnet's moving this direction, it's cutting the wire at the maximum angle, perpendicular. Therefore, it's creating a maximum amount of voltage. Whenever I'm going this direction, it's the opposite of this. So now I have negative maximum amount of voltage. Whenever I have my magnets moving in this way and this way, they aren't creating any voltage whatsoever because their magnetic lines are not perpendicularly intersecting my conductor. Does that make sense? Why, as I go around and around, I have points that I have high voltage that's positive. I have points that I have a high voltage that is negative. And I have 2 points that I have 0 voltage whatsoever. So I start out with 0. I'm moving in this direction. As I go around, I start to cut this more and more and more. And by the time I cut it in a perpendicular format, I am at my peak voltage. Now I begin to go down, and eventually I am at the same perpendicular or parallel to it. I'm back to 0. Now I slowly begin to turn, and I'm going the opposite direction. I'm in negative voltage. I reach my peak of the negative voltage. I'm down here, and then I return back to my parallel angle to here. I've made one complete rotational cycle, and I have gone from 0 to peak voltage to 0 to peak negative voltage and back to 0. This shape was created because we created electricity through rotational generation. All right. That's why we use the sine wave. So alternating current does not have to be in an actual sine wave, though. It could be in square waves, or stepped waves, or modified square waves. In fact, the inverters are sometimes rated in those terms. This is a modified square wave inverter, probably a cheap inverter, all right? But they're out there still, especially for off-grid applications. For grid-tied applications, you have to have a sine wave inverter. There's no option about it because the grid has a sine wave, and to match that, it's got to produce a sine wave. But for off-grid applications, modified square wave inverters are still out there. They're on the cheaper end. So to start with, we'll look at the, my colors are already getting me. The middle color here, I believe that's green, isn't it? Okay, so with a square wave, we start at 0 and instantaneously we jump to our peak. And we stay at our peak for a certain amount of time. Then we drop immediately to our negative for a certain amount of time. For a square wave inverter, it doesn't have to have a real high peak or a low peak. Basically, if I had 10 batteries in a row, and I had this little thing that I could spin at a certain speed, and it would go from positive, negative, I could hand crank a battery and create an AC 120 volt signal, as long as I spun it at the right speed. All right, on, negative, positive, negative, positive, negative, positive, negative. There is no downtime in here. With a modified square wave inverter, I have a little bit of nothing, and then I peak. But because I have a little bit of nothing in here, I'm going to have to be higher than what I actually want to operate at to overcome my losses in here. All right. And so once I have modified it for a certain length of time, I can still have the same amount of power. Guys, if you did the math, the area underneath this sine wave and the area underneath this modified square wave is exactly equal to the area underneath the sine wave. They all have the same area. That area is representative of the power that they produce. Right? Higher voltage, higher current. Volts times amps equals power. So as my voltage goes up, my current flow would be going up also. All right. Questions over a sine wave, square wave, or a modified square wave?
So with square wave, I think I'm remembering that it can damage some of the appliances and stuff, right?
Absolutely. Even a modified square wave can damage induction appliances, induction motors. And so if you are trying to create rotational energy, it is very, very necessary to have the true sine wave for an efficient rotational energy production. Otherwise, you're going to have losses, significant losses. Those losses show up as what? Heat.
Oh, because due to the duration of that time.
Yeah, it's putting the power in.
Yeah, too long.
There you go.
And then. So,
that's right. That's exactly right. Yep. And so that additional heat buildup will make the motors go bad. Yep. And the other sometimes issues, they just don't have the true torque or the energy that we need. See, this modified square wave still close to reaches the peak, but the sine wave really does have a higher peak, and that higher peak would mean more torque, to get something started. So if your motor already struggled to get the load moving, man, that square wave might just burn that motor out. Yeah. All right. So modified square wave inverters, it is a stepped waveform that approximates the sine wave. In other words, if I was going to do a stepped form to look as close to this as possible, I would actually do this. Oops. And we can keep going right on around there. Okay, I can have theoretically thousands of steps, and I can very closely approximate this shape with the use of diodes, transistors, thyristors, and capacitors. What we are actually able to do is take the wasted energy in here and store it in a capacitor to be released up here. Our modern inverters are 90, sometimes as much as 98% efficient. Any extra energy that they've got, they stick it in a capacitor for 1/60th of a second and then let it back out of that capacitor later on in that cycle to be used. They're very, very good at not wasting the energy. Okay. The term quasi sine wave, I don't like. It's misleading, but it is still fairly effective. Anything that would be listed as a modified sine wave or a quasi sine wave would be approved to run, induction motors. Though you're not going to burn them up. Not going to be quite as efficient. Right, right. Okay. They have a clearer signal than a square wave, but still, even modifieds can cause RF noise in TVs and radios. They should not be used for motor speed controllers. They should not be used with a battery charger if it doesn't have its own internal transformer inside. So frequency is the number of waveform cycles per second. It's expressed in hertz. You do want to know that the units for measuring frequency are hertz. All right, that's something that you will be quizzed and NABCEPT on. In our system, we use a 60 hertz inverter, always. So there are 50 hertz inverters that are on the U.S. market. Why? Why is it if you went on eBay right now and looked that you're going to find 50 hertz inverters along with 60 hertz inverters?
Because they bought them from Europe and brought them over here to sell.
They didn't buy them for Europe to bring over here to sell. They bought to run European appliances. There are scientific instruments and European appliances that are much better made than the American units, and so either you'd have to have a frequency converter. Basically, it's a battery that would just, a rectifier that turn it in, yeah. Or you're going to have some type of a device that will output 50 hertz. So have you ever heard of Electrolux appliances? They're European made, and it's against the law in Europe for products to be manufactured using planned obsolescence. So if you want to buy appliances that are going to last forever or last a long time, European appliances that use a 50 hertz system are one of the few ways to get those high quality appliances. They don't make them in 60 hertz because they're not that common on the US market, because by the time you ship that cook stove over here, that's a lot more money. And then it's a niche market. Pretty much the only people that want those are commercial applications or Europeans who have moved over here. Guys, be careful. Be careful buying inverters off of the internet that's not from a supplier, because that's a lot of times why they're so cheap. I almost bought a 5,000 watt inverter, brand new in the box, Sunny Boy, on eBay for like $600. Normally it'd be like $3,000. The last minute, I asked them to send me a picture of the spec sheet to make sure, like, I want to see your actual owner's manual, and I noticed it said 50 hertz on the system. Okay, so I don't know how it got here, but he was just trying to sell it. He claimed, I don't know the difference in the hertz. Yeah, don't know about that. So period is the time it takes for the periodic waveform to create one full cycle. The period is the inverse of the frequency. In other words, if the frequency is 60 hertz, then the period is 1/60th of a second. Period is measured in seconds, right? Or time. Magnitude. Magnitude is the maximum absolute value of a waveform. So The peak voltage is relatively important for off-grid inverters. Obviously, for grid-tied inverters, your peak voltage is going to have to match whatever the voltage of the grid. I think you guys might be surprised at how much variation a lot of inverters have. Some inverters are capable of outputting as little as 220 volts and as much as 480 volts. They can put out 208 in between. They can match 220, 240, 230, and all the way up to 480. But every inverter has a maximum voltage. Cannot go any higher than that. And obviously you can't hook it up to either loads or the grid at a different voltage. I would say that I would discourage you from using transformers to change your voltage. What do I mean? Hey, I made a mistake. I ordered 240 volt inverters, and I figured out when I went to install them that this company has 480 volt electricity. Okay, I can just put in a transformer to turn 480 into 240 or 240 into 480. Well, number one, that's one more part to break in your system. It's another part to buy for the system, but you're going to have losses. And that's the bigger part, in my opinion, is get the equipment to match the voltage instead of buying extra equipment that you're going to have losses at. Peak to peak is a measurement between the positive and negative maximum voltages. We've already talked about that. Root mean square is a statistical parameter representing the effective value of a waveform. In other words, the RMS, the root mean square, is the effective voltage of the system, or the effective current of the system. DC equivalent is an easier way to explain it in my brain. Three-phase AC power. Now, this is a concept that until I saw some charts, I really didn't grasp. How can I have three different phases of electricity, yet I only have three lines, three wires? All right. It's kind of crazy to think that with 240 volt standard electricity, I have two wires and I only have one phase. But I can add one more wire to that, and I've created two additional phases. And it took me a long time to understand that. All right. And then it was explained to me that if I take a circle, I cut it into three equal sections, I have 120 degrees, 120 degrees, and 120 degrees apart from each other. Make sense so far? Now I take a coil of wires and I put one coil at each of those sections. All right. Now I put a big magnet around this and I begin to spin that magnet. Now, notice how over there we have a whole drawing of a whole circle. Guys, that circle is just happening all along this line right here. So when the magnet comes through here, it's doing the same thing. It's cutting them in this direction, and then it's cutting them in that direction, and it's cutting them in that direction, and it's cutting them in that direction. But it's doing that during the whole cycle. So this has its own signal that looks like that. This has its own signal that looks like that. And this has its own signal that looks like this. The difference is they're all 120 degrees apart from each other. Therefore, when these two, this has a positive maximum, and this has a negative maximum. What do we mean by that? Okay, I've got I'm sorry, I didn't have that right. I have a negative middle and a negative middle. What do I got? Okay, I got phase one. It's at its peak, positive. Phase 2 and phase 3 are both halfway negative. 0.5, 0.5 negative adds up the same as 1 positive. Okay? No matter where you go in this cycle, there is an equal amount of positive voltage from 2 of these as there is a negative amount of voltage on the third one. Or there is the same positive amount, negative amount of voltage on 2 of them as positive on the third one. So what's happening as the rotational generator moves around, the electrons that are forced out of this coil go through a load and come into this coil. And then by the time they're pushed over here, they're pushed out of this, through load into the other. So I have a different voltage between each of these coils. So I have a voltage between 1 and 2, a voltage between 2 and 3, and a voltage between 1 and 3. I have 3 wires. I have 3 separate voltages that are each in 3 separate balanced phases with each other. So literally, the magnets are pushing the electrons out of this coil, through the load, into this coil, and as they rotate, they go back out of here, through the load, and into this, and they just chase around. What's the advantage of this? There's no point in this cycle that is 0. If I just look at any one of these, let's look at the black one, because I like black. Right here is 0 volts. There's no work being done. So in this rotational cycle, I'm giving it gas on my car. Even though it's got full fuel, there's no voltage. There's nothing happening. I have no actual work being done. Wait a minute, if I have 3 phases, at this point where this one is doing nothing, both of these other 2 are doing something. So there is never a point that I don't have an even power production occurring on a 3-phase system. Does this make a little bit more sense about how a 3-phase system is created and was created originally? So we also have what's referred to as a neutral in a 3-phase system. And the 3-phase neutral would kind of be like the return. It would go to the middle of this. So it could come out of this and return to here to the neutral. It could come out of this one and return to the neutral. And so if I have, let's say, 240 volt difference right now at this cycle between here and here, then I would only have 120 volt difference between either one of these and the neutral. All right. So there's more than one way to wire a 3-phase system. I believe that we do briefly touch on that. But for an inverter, guys, it's actually really easy to wire a 3-phase inverter. You have 2 wires that are referred to as hot wires, and one that is referred to as the neutral wire, a 4th wire that is referred to as the ground. From the grid, I would have 3 wires that are hot, 1 wire that is neutral, and 1 wire that is the ground. Inside of that inverter, you've only got 2 wires that are hot, 1 that is a neutral, and 1 that is a ground. So inside inverter 1, I run wires from phase 1 and phase 2, and the neutral and the ground. In inverter 2, I wire phase 2 and 3, the neutral and the ground. And in inverter 3, I wire phase 1 and 3. And so even though the 3 inverters are outputting in 3 different cycles, one of them is outputting at the same time as that the other one is not. But they're all 3 handle one of the legs of the 3-phase system. Questions over 3-phase? A common question is, go ahead.
Well, just how common is solar 3-phase?
Virtually any commercial system is going to be 3-phase.
Commercial on that.
Yep. Residential 3-phase systems are only happening for farmers. A lot of farmers have grain bins that need 3-phase electricity. Even though they don't use that much power, they need the 3-phase. But even then, if they have a 3-phase converter, a lot of times, if they have single-phase power that comes to their house, then they have a 3-phase converter that turns that single phase into into 3-phase. You can't put a 3-phase inverter in for that customer if they have single-phase grid connection. So in the event like Crowder, we have 3-phase. all right, then it's smarter to buy either 3 single-phase inverters or 1 3-phase inverter. There are inverters that output 3-phase from 1 inverter. Those are cheap. Anytime that you can go with a 3-phase inverter for a project instead of 3 single-phase, do so. We have a customer right now that is putting in a 20 kW system, but they do not have 3-phase electricity at their location. I could buy a 32 kW inverter cheaper than I can buy 20 kW of single-phase inverters for this customer. And so 3-phase inverters, they're larger, normally 30 kW or bigger, but their cost per watt is significantly lower. And they're really easy to wire. I'll just tell you that. A lot of people get intimidated, like, oh, it's 3-phase, I don't know how to wire it. They don't even care if it's a 3-phase inverter. They don't even have you label which phase is what. It's just hot wire, hot wire, hot wire, neutral wire, ground wire, monitoring, and that's it.
But you can't have a 3-phase inverter if.
You don't have a 3-phase grid. Yep.
And out in the country most of the time.
Correct. Yeah. Okay, so power quality is the measurement of how closely the power in an electrical circuit matches the nominal values for parameters such as voltage, current, harmonics, the power factors. In other words, this is supposed to be 120 volt AC in our walls. Occasionally when we check it, I've seen it as low as 116. I've seen it as high as 128. All right. So the power quality is how close do we actually stay to that 120 volts or 240 volts or whatever the load is. Voltage sags and swells. Voltage sags overload transformers and circuits. They have problems for long conductor runs. Why? Well, your loads have to use a certain amount of wattage. It's not just current, it's wattage that they need. Okay, I got a refrigerator, it needs 1500 watts, and I've got a 14 gauge wire that's running to it. Suddenly the voltage sags on the electrical system, and instead of being 120 volt AC, it's now 90 volt AC. Well, the amperage to operate that refrigerator is going to have to go up by about 30% because the voltage went down by about 30%. Is that 14 gauge wire capable of handling 30% more amperage flowing through it? It might not be. Okay. And so that's where long conductor runs or small conductors are troubled during voltage sags. Question? No? No. What causes a voltage sag? Large loads being turned on simultaneously. Like we had a power outage, and now Lazy Boy's coming back online. Every time they kick on a big piece of equipment, we would actually be able to watch the voltage drop in our system over here at Crowder. Okay? And so when do we see large loads that get turned on? Well, in the mornings when factories start, and when shift changes happen, or whenever we reach certain temperatures and AC backup units or backup refrigeration units begin to kick in. Like, let's say that you're a factory and it's okay for working all the way up until 80 degrees, but your parts have to stay under 80 degrees. Well, suddenly it gets to 80 degrees and you have a large AC system kick on. That non-normal large load could affect the other loads in the building, all right, which could cause problems for them. We also have voltage swells, and voltage swells can be caused by large loads being turned off. All right, factory shuts down, they flip a switch, and everything turns off. All that electricity on the grid that was being used to power that factory, now where's it going to go? Well, it's going to go to the other places, and you're going to have a voltage spike or a voltage surge. This can also be caused by storms and induction. I got electric lines that are hanging in the air, and the wind comes and it starts to blow them. All right, they have a magnetic signal around them. As they move closer and farther to each other, those magnetic waves are going to cut the other conductors, and change the voltage in those conductors. Sometimes it's called ghost voltages. Like, hey, this line, this wire isn't connected to anything, yet I've got 4 volts of power in it. Why? Because there is an existing line that has AC power running in the same conduit, and every time it comes on, off, on, off, on, off, it is creating or inducing a voltage in the other conductors that are in that conduit. That's part of the reason that there's maximum fill rates for conduits. All right. It's also a really big reason that you can never, ever, never run DC conductors in the same conduit as AC conductors, because those DC conductors would 120 times per second be negatively affected by the AC voltage changes. So when we have storms and we have electric lines that are being blown in the wind, that can actually cause both voltage swells and sags. Unbalance occurs in 3-phase power supplies. If one of these coils was slightly damaged, the voltage coming out of it could be slightly different. Over time, you have equipment that wears out and needs to be replaced. If you ever have a slightly different voltage on one of the 3 phases, that can cause some problems, especially for efficiencies. Then that would be referred to as a voltage unbalance. If you ever lose one of the 3 phases, you now have 2 phases, right? No. Remember, I have 3 wires. As soon as I lose one, I only have 1 phase, the phase between these 2. There is no such thing as 2 phase. It can't exist in a safe environment. Okay? To have 2 different phases, I'm going to have a 3rd wire. If I have 3 wires, then I have 3 phases. Okay? It is possible, though, that one of those goes down, and that is referred to as single phasing, the complete loss of 1 phase of a 3-phase supply. Blown fuses are the most common problem for that. Mechanical switching failure or lightning. Other things about power quality is current unbalance. If I have a voltage difference, won't I automatically have a current difference? Yeah, unless magically the resistance has varied to change that. But if all things are the same, I got a 3-phase motor, I got a higher voltage on one of these 3 phases, that means I'm going to have a higher current on one of those 3 phases also. All right. Oftentimes, what's happening is one of the phases has a lower voltage, so the other 2 are trying to make up for that loss in that cycle, so they end up having a higher current demand. They're asking for more power to make up for the loss of power in one of the 3 phases. And then last, phase imbalance. Phase imbalance cannot occur from a rotational generator. Our grids have rotational generators, so we can't have a phase imbalance. The only way that phase imbalance can occur is if you have a computer that is generating this. Let's say you have an off-grid or standalone 3-phase inverter. There's nothing that is physically 120 degrees apart from each other. This is just a computer that's timing itself. Phase 1 and 2, phase 2 and 3, phase 1 and 3, phase 1 and 2, back and forth. I mean, I'm human. My timing gets off. Timing on inverters can get off also. A lot of times, phase imbalance can be solved by turning all of the inverters off, disconnecting them from any existing power sources, de-energizing them to where there's not even a stored power, and then starting them back up. Almost always, that will fix the problem. If not, it's probably going to be a warranty issue. Harmonic distortion. It's easier to understand harmonic distortion, I think, whenever we look at a chart. Okay. This would help describe harmonic distortion. It's whenever the wave patterns are not balanced in one form or another. I'll pick on Randy. What's symmetry, Randy? You taking a nap on me? What's symmetry? She's really attractive. She's symmetrical. What does that mean? Mirror. You could cut it in half, and one side is identical to the other. We are supposed to have symmetry in multiple ways on our sine wave. To start with, we're supposed to have a vertical symmetry, same distance above as below. We're also supposed to have distance symmetry. How far is each of these? And so, anytime that you do not have appropriate symmetry, then you have harmonic distortion. Certain appliances, this makes no difference on, like your well pump. Your well pump could operate from probably 50 hertz or 45 hertz to 70 hertz. It could operate from 110 volts all the way up to probably 260 volts, because it was made to handle those situations. Guys, computers a lot of times don't like harmonic distortion. Like, they have a processor that needs a constant signal. And if they don't get that constant signal, they don't function right a lot of times. You can actually ruin fine, detailed electric circuits. They don't have proper harmonics. All right. Let's see my time. Okay. All right. Now, this next term, the power factor, I'm not going to quiz or test you on, and I do not believe that NABSET quizzes or tests you on, but I kind of want you to understand the concept. It is the ratio of true active power to apparent power. It describes the displacement of voltage and current waveforms in AC. So let's go back to this. So apparent power would be all of the space underneath the green box. True power would only be the part of the green box that is also within the blue area. This area here is wasted. This area here is wasted. All right. It's why closer to a sine wave signal that we can create, the more efficient the inverter will be. If we go get a cheap little like $200 inverter that just hooks up to a 12-volt battery and you look at the efficiency of it, it's probably going to be like 85% efficient. It's not going to put out a true sine wave. Might not even be a modified square wave. Might just be square wave, and that's it. Why is it so inefficient? Because all of this extra energy that is not used by a normal standard appliance is just wasted. It's dissipated as heat, and therefore it is highly inefficient. There we go. Okay, and so AC loads are either resistive or reactive. Let's explain resistive. We understand resistance to the flow of electricity. I have a heating element and a hot water heater, and that is a resistive load. To push electrons through it takes a certain amount of voltage, and if you have 10 electrons or 10,000 electrons, being pushed through that element is taking and outputting heat. All right. If you hooked up a 12-volt battery to a resistive load, it would still partially function. Like that heating element, the heating element's going to get hot. Even though it's rated for 120 volts or 240 volts, it will still activate as long as you have enough voltage to get through there. All right. A reactive load is actually using magnetism. I've got a motor right here. I start to put electrons through this coil, and magnetism is created, and it pushes that in a rotational cycle. Well, that magnetism is not created by the voltage. It is created by the physical flow of electrons. And that is a delayed response. The electrons are only moved by the voltage. Okay, so I start with 0 voltage, and now I begin to increase the voltage. Therefore, the current begins to increase at a gradual pace. So as that current begins to increase, then I begin to create a magnetic field around the conductors where the current is flowing. That magnetic field being created is affecting either other magnets or other magnetic fields within this inductive load. That induction is delayed. It doesn't match the cycle of the AC waveform. All right. So if I have an inductive load, I need to have a sinusoidal waveform, or else I'm going to have a whole lot of wasted, not true power. Okay. That wasted power is going to show up as heat, and it could potentially damage appliances, motors, and even have a signal interference, like keeps your radio from being able to pick up the proper signal. Okay. So a resistive load keeps the voltage and the current waveforms in phase. A reactive load that uses inductance or capacitance causes the voltage and the current waveforms to be out of phase from each other. Again, you're not going to be quizzed on these from me, really. The main thing I want you to understand is that inductive motors, inductive loads, reactive loads, their phase of current is out of phase. All right. My wife telling me she just put stuff in the car. Okay. Again, true power is the product of in-phase voltage and current waveforms. It's real or active power. And reactive power is the product of out-of-phase voltage and current waveforms. There's a little chart that kind of shows this. Apparent power is the combination of true and reactive power. Basically, what did I actually get accomplished? Or what can I actually get accomplished? All right, so inverters. Inverters are devices that convert DC power into AC power. There is an energy cost to invert, always. All right, you're always going to have losses. Those losses are going to come in the form of heat. Early inverters were electromechanical. I had an electromechanical inverter, and I may have given it back to my dude that I borrowed it from, so I want to check just to make sure I don't still. So I had a buddy who bought a 1970s ambulance. Inside the ambulance, there was AC equipment that needed to be operated. So whenever he retrofitted the ambulance, he's a glass blower for a living. He blows custom glass pieces. His number one clients are marijuana dispensaries that sell, pipes and bongs and things like that. And so he goes to festivals and he has his ambulance that says EMG on the side of it, emergency medical glass. And he does glass blowing events right there at his ambulance. So he needs power to operate his, his glass blowing equipment and everything like that. And so the inverter that it had inside of it was a DC motor that ran off of the 12-volt battery that was powered by the alternator, which was powered by gasoline. It had a shaft, a metal shaft, that went to an AC generator that would generate up to 20 amps and 120 volts. Those mechanical connections are outdated. They are highly inefficient. And to be honest, the only type of a system in existence today that still uses that is three-phase to single-phase conversion. You have a large three-phase generator, and you are needing to convert that into single-phase. You may have a three-phase motor that then turns a single-phase generator. Modern inverters are referred to as solid state. I need you to know that term. Randy, wake up. You're missing things. Can't wake him up. A solid state inverter or a solid state electrical device means that there are no moving parts. You absolutely need to know that, and it is extremely important. Why is that a big advantage?
It doesn't break.
Thank you. stuff that moves breaks in time. And our solar panels, they don't have moving parts, so they lasted forever, not forever, for a very long time. Our inverters have gotten better and better and better. Whenever I started inverters in 2009, inverters had a 5-year warranty, and you could buy an extended 10-year warranty that would add about 25% to your cost. Today, inverters almost all have a 10-year warranty, and you can buy extended warranties up to 20 years. The average inverter that fails today is 14 years old. I know that that's a weird thing to tell you. That's not saying that the average inverter made today will only last 14 years. It's saying that the inverters that were made 14 years ago only last an average of 14 years. I do believe that the inverter is one of the weakest links in the PV chain, especially for grid-tied systems. If you're going to have a failure point, the inverter is the most likely chance for a failure point. I do recommend buying extended warranties on the inverters. Normally, it's only about a 10% cost addition to add 5 years additional. So you want a 10-year warranty, you got an existing 10-year warranty, you want a 15-year, add 10%. You want a 20-year, add 10% more to that. Inverters are getting cheaper. That is for sure. So they can broadly be classified as either standalone or utility interactive. A standalone inverter is powered by batteries. It's connected to batteries as the DC power source, and it operates independently of the PV array and the utility. In other words, a hailstorm comes and destroys my PV array. It's not going to affect my standalone inverter because it is powered by the batteries, not the array. Utility interactive inverters connect and operate in parallel with the utility grid. They are powered by the array, unless they're a bimodal inverter. All right. Bimodal inverters can operate in either interactive or standalone mode. And an AC module inverter, it's a microinverter. It is a small interactive inverter that is wired specifically to each PV module, and it is only permitted in interactive operation. Now, there's this weird conundrum that some off-grid people are starting to do, and that is they buy and they build an off-grid battery-based system. But during the day, they want to run their air conditioner. And their air conditioning load is so large that it has a tremendous drain on their batteries and on their PV system. So they install an additional array with micro inverters on it that is connected to their existing system. It will only function and come on if the if the system is using more power than it needs. Does that make sense? So I hate that concept. I think you're just wasting a whole lot of energy to do it. And that's the reason that I will teach my students you only use microinverters to design for grid-tied, utility interactive systems. Period. Don't try to get fancy and say, hey, I'm going to use a few of these grid-tied inverters for an off-grid system during the day because it works all the time and it will help power these loads. Well, all it takes is one time for that to be shut down, and you're just wasting your power. There's nothing happening. All right. So the switching devices inside of the inverter, DC power is switched to create AC waveforms. We're going to talk about how that switch works here in a few slides. An H-bridge is what it's referred to as, but it is a solid-state switching component that includes thyristors, transistors, and diodes. All right. The switching control, all inverters are either line commutated or self-commutated. Some inverters are smart enough to be both. So If you have a line commutated, the switching device is triggered by an external source, the grid. When the grid goes positive, the inverter outputs positive. When the grid puts negative, the inverter outputs negative. It matches the electrical signals that it is receiving. It boosts and puts more of that same signal right back into the grid. However, that won't work if there is not a grid. The inverter is not getting a signal, and so it doesn't know what to do. In fact, if it goes for more than 120 cycles without a signal, it turns off. That's anti-islanding protection. Okay? A self-commutated has internal control of the switching device. In other words, I have an AC refrigerator that's plugged into a battery-based inverter. That inverter has to know how often to switch its directions to power that refrigerator. And so that self-commutation is where either the 50 hertz or the 60 hertz comes into play. Square wave inverters, the first step to converting DC to AC is turning it from a straight line DC signal into a square waved AC signal. It is not very efficient, it may damage certain loads, and it is simply an H bridge and push pull circuit. We'll look at what that means here in just a couple minutes. But then more fancy inverters go to low frequency waveform control. It converts the square wave into a modified square wave. Multiple square wave inverters in parallel can create a multi-step modified waveform. These still are not real efficient. Okay? High frequency waveform control. It's referred to as pulse width modulation, is used to switch at high frequencies to produce sinusoidal waveforms. It is very efficient. All right. Basically, we turn it on, we turn it off. Turn it on, we turn it off. We turn it on, we turn it off. We do that at just the right speed and for the right duration that capacitors always retain an output, the amount of voltage that's necessary to either match the load's needs or match the existing grid signal.
So I've heard that if you have stuff that has high startup amperage, you want low.
You want what?
A low frequency.
I've never heard that. Yeah. Yeah, I've never heard that a low frequency waveform would be better at high startup loads. So it's possible. I think that it matters if they are, I'd almost think the opposite, man. Because you know that those high startup loads have to be induction loads, which means they really need the most sinusoidal waveform possible. So you might make sure you didn't flop that in your brain. Because I would think that high frequency waveform control would be the required one for high startup loads. Yeah. So a lot of times we have what's referred to as a PCU. It's not a personal computer unit. It's a power conditioning unit. And this is components that, and I say components because there's always multiple components. That the whole goal of these components is to make the power quality, remember we talked about power quality, as high as possible. So your power conditioning unit would be an example of an MPPT. That's what I like to use as the perfect example of a power conditioning unit. It's a smart thing. It changes its resistance to the conditions that it is being presented. All right. The whole goal of power conditioning units is A, to make sure that the power that is produced is not going to harm the loads. In other words, it matches the load's needs, whether that's the grid or your refrigerator. And B, that it makes it as efficient as possible, that we don't waste power unnecessarily in converting it to a signal that matches the Many of these power conditioning units can contain self-monitoring and protective features. You know, they don't want something to break, and so the power conditioning unit is one more step to making sure that if we get to too high or too low a voltage or current conditions, that it will turn off and deactivate. So this is probably, in my opinion, the most important slide and part that we talk about to understanding inverters is understanding how an H-bridge circuit works. An H-bridge circuit is the circuit that turns AC power into DC and DC power back into AC. It just depends on what you're wanting to do with it. All right. It has four switches, and it connected to one load. So this is the load, an M. Anybody tell me what that M would mean for an electrical schematic? Means motor. So it is a motor that is in that. Okay. It could be a light bulb. It could be a battery. It could be whatever you want it to be. But this center thing is the load. This is the thing that we are operating right here. All right. And so in this, I've got positive and I've got negative. All right. So I'm going to follow the flow of electrons from the negative, bloop, 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 and they get to here. S2 and S3 operate simultaneously. S1 and S4 operate simultaneously. Meaning, if S2 is closed, S3 is closed. So let's follow our path of electrons. I come out of my negative, bloop, 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 bloop. If S2 is closed, I go over here. I can't get through S1 because it's open. So I have to go through the load and back. Notice the flow of electrons was from left to right. Everybody follow me with that? Okay. Now I'm going to reverse. I'm going to open S2 and S3. I'm going to close S1 and S4. Now my electrons are coming along. Hey, they can't go through there because it's open. So they come through here. They can't go through there because it's open. So they have to come through here. Now my electrons went through this load in the opposite direction. All I have to do is have S1 and S4 open at the same time as S1 and S3 close, and vice versa. And then I have to open and close them 120 times per second, and I have just turned DC electricity into AC electricity. It's really a pretty simple device. All right. Now, all I have to do is reverse that process to go back from AC electricity to DC electricity. The difference is, what would the charge rate actually look like? So if I was going from DC to AC, let's say I had a 12-volt battery. I'd have 12 volts, 0 volts, and negative 12 volts. I'd be coming along at 12 volts, and then I would reverse, and then I would immediately drop to negative 12 volts. And then I would reverse, and that's how my waveform would look like with an AC output. Now, let's say that I had a waveform like this, and I wanted to run it through this device to turn it from AC into DC. I can do that, but it ends up looking like this. Zero volts, 120 volts, for example. I can charge a battery very easily with this, guys. So rectifiers that are powered by AC waveforms, they're actually charging batteries in pulses. Pulse off, pulse off, pulse off. Now, I can actually turn it off from here to here if I wanted to. I could leave those circuits open completely. So I can vary the length of time, the pulse that I'm charging this battery using this same H-bridge circuit.
Cash.
Yeah.
If you leave cash.
Correct. That's exactly right. Yep. Any questions on how an H-bridge functions? little simpler than you might have thought, isn't it? Yeah. Okay. Well, I'm going to go ahead and stop my my recording right here. Thanks for joining me, guys, and have a great day.